Hi, welcome to part 2 of resolving forces, looking at using our resolving forces skills to solve practical real-life problems. So here we have Cedric's truck. Now looking keywords within this, it's kept stationary. So the forces in any direction, this direction, or if we wanted to take this direction, equate to 0. Okay, so resultant of those forces is 0. Now, what we're going to do is we're going to look at resolving the forces in two directions. As I've just shown, these two would be the perfect directions because it saves us having to resolve 3 of the 4 forces. If we resolved vertically and horizontally, then I'd end up having to resolve this one, and this one, whereas at the moment I just need to resolve this one. So we're going to resolve parallel and perpendicular to the slope. Now let's look at resolving parallel to the slope, and up the slope we have 10,000 newtons. That is equal to the forces down the slope, which is the resistive force X plus the component of this weight in this direction. Now if we imagine a line out here, this angle is 20, so this component is cos, this component must be sine. So the component of the weight in this direction would be 1000 G sine 20. Now we have a lovely equation there with x being the only unknown. So we can solve that little puppy and get x is equal to 6645 newtons. Okay, so I've resolved in this direction, parallel to the slope. I'm now going to resolve in this direction, perpendicular or at 90 degrees to the slope. Let's move that down a little. Okay, so acting up, I have R, and the only force acting against that is the component of this weight in this direction, which we've already seen is cos. So that's 1000 G cos 20, and from that we get the value of R to be 9218 newtons. Now we're also asked to find the coefficient of friction, mu. Now we've missed out a sentence here or somewhere in the question which should have said the truck is on the point of slipping or on the point of moving. If it's on the point of moving, or if it's actually moving, then friction is maximized. So the frictional force is equal to the coefficient of friction between the two surfaces. In this case that's the wheels of the truck and the slope, multiplied by the normal reaction. We know that the frictional force is 6645 because we worked it out over here, and we don't know mu, and we know that R is 9218 because we worked it out here. So from this we get that mu equals 0.72. The larger the value of mu, the rougher the surfaces, the more friction between the surfaces. Okay, let's look at another example. We have Amelia pushing horizontally on this block. She's pushing with steady speed. So the block speed is not changing, therefore in any direction we take, the sum of forces is 0. Now what I'm going to do here is just highlight these two. Last question, we resolved perpendicular and parallel to the plane. In this question we're going to resolve horizontally and vertically because it means that that R there is the only force I need to then componentize. Right, let's get rid of all these red bits. Okay, so steady speed, forces equate to 0. Let's look vertically, shall we? I have a component of R in this direction. This angle is 30, so this component moving through the angle needing your swimming costume is R cos 30. The only force opposing that downwards is this little puppy here, which is 20G. So I have an equation just in R which I can solve very easily to get R is 226.56 newtons. Now I've kept that to 2 decimal places because I know that I'm going to need it in the next part of the question. So rounding too much here would be silly and would lead to further rounding errors later on in the question. X is acting here, this direction. R also has a component in this direction. So let's equate those two. X must be equal to the R component in this direction, which here it was R cos, here must be R sine. So that's equal to R sine 30. Now we've just calculated R right here. So we can easily find from that that X equals 113 newtons. Key points for these two questions have been: look at the directions you want to resolve in. It's not always horizontal and vertical. Sometimes it's perpendicular and parallel to the plane. Sometimes you have a plane, a slope here, and you're still resolving horizontally and vertically. Just try and do whatever's going to mean less resolving of forces for you. Okay, as always, thank you for listening.